Right. Hello, guys. Congratulations. We already reached the last section of the chapter. This is the eighth section, the Lagrange multiplier. So this is sort of a consecutive section from our previous topic on the maximum and minimum value. Basically, in this chapter, in this section, we want to investigate this type of optimization problem, which is optimization with constraints. And this is actually a very common problem that shows up in different areas of math. For example, there is economic problems, there's physics problems, and those are generally optimizing problem over some constraint. So precisely speaking, we're simply maximizing some function over some constraint. For example, I want to maximize, say, x plus y over, say, x squared plus y squared is 1. So you have to find every point on that particular circle that which points that maximize the corresponding function. And you can also minimize some function over like multiple constraints. So there's very many different flavor of the constraint problem, and these are one of them. So unlike the usual maximization and minimization technique, which we introduced in the previous section, you cannot just differentiate and find a critical point. The reason is that the critical point might not be on the corresponding constraint. For example, if the function, say this function is x plus y, and say this is x squared plus y squared plus equals to 1, then to find a critical point, okay, say maybe this guy. Maybe let me do, okay, 4. Then the differentiation, sorry, the gradient will be something like 2x 4y cubed, and the only critical point is 0, 0, the origin, right? However, you can see that the origin is not on a circle because 0 squared plus 0 squared is 0. So this is the reason that we have to develop a new technique on studying this type of constraint optimization problem. And that technique is called the Lagrange multiplier, right? Okay, so let's start with the theorem. So Lagrange multiplier is stating this kind of theorem. It states that when f and g are both differentiable function, obviously I choose r squared, but you can do something like r cubed, anything in high dimension will work. And suppose that f achieves a local extreme, it doesn't matter whether it is local maxima or local minima, subject to this constraint. So x and y satisfies this constraint, g of x, y, and z. And over those x, y, there is a particular point, a, b, so that f achieves a local extreme on a constraint. So basically, I'm saying that g of a, b must be c, and that among all x, y that satisfy g of x, y being c, g of ab, f of ab is one of the either local maxima or local minima. Now, with the additional assumption that the gradient of g of ab is non-zero, then we claim that the gradient of f is parallel to the gradient of g. So first of all, that is kind of look this theorem in a different way. The first thing is that how does this help us to solve the constraint maximization or minimization problem? So basically, this kind of equation provides you another system of equation to study the critical points. You can find out the critical point using this equation. This is how this benefits us on the solving of the optimization problem. And geometrically, what does this mean? So let us recall that what is gradient of g? Gradient of g is actually a normal vector of this curve, right? Suppose g of xy, the level set of this curve looks like this, g of xy. This is g of xy equal to c, g of xy equal to d, maybe like that. Then the normal vector is actually gradient of each point, right? So why is this happening? Why does the gradient of the target function is parallel to the gradient of the g? It is kind of intuitive in a sense that you want the function actually tangent to our curve, right? So when you're tangent, that means that you share the same normal vector. So the gradient of f and the gradient of g are parallel, okay, geometrically. I can include some graph afterwards, but that is the geometric interpretation of this theorem. But computationally, you should understand that this kind of equation provides you a more of a restriction on how you can solve the critical points. The points that satisfy the constraint which f achieves a local maximum or minimum. Okay, right. So this theorem basically depends on the implicit function theorem. So let me go through this quickly. Suppose first that obviously the gradient of g is non-zero, that is the assumption. So we can assume, say, gy is non-zero. Of course, you can perform the same algebra if we're doing gx. But suppose gy is non-zero, then we have that y is locally solvable for x, right? Y is equal to this is pronounced phi. Y is equal to phi x locally near the point g of xy being c. Okay, so it's the curve g of xy being c, and at some point, okay, maybe I can show it better. This is the curve. At this point, the tangent is non-zero, so you can locally solve the function y in terms of some functional graph. Okay, so locally this curve looks like it. Sorry, I'm saying this incorrectly. Locally, this curve looks like a graph of a function where the function is given by y equals to bx. Okay, and in particular, also by the implicit function theorem, we know that the differentiation b prime of x or dy dx can be represented by minus gx divided by gy, right? Okay, so now we have our setting done. Let us try to compute the gradient of the function f. So we know that f achieves a local extrema on this curve, right? Sorry, on this curve, and in particular also this curve. So that means that if I plug in x and phi of x inside of f, then this function h of x should achieve a local extrema at the point x equals to a. Obviously, phi a is b, right? The point that we suggest here. Okay, so now you reduce to a single variable calculus. Having a local extrema means that h prime of a is 0, right? You'll always have a horizontal tangent at the point where you achieve a local extrema. So by chain rule, you have fx a phi a and fy a phi a, and then phi prime of a equal to 0. So that tells us that you can solve fx in terms of minus fy phi a. So the gradient of f, maybe I can write more step, is fx fy, where fx is equal to this guy. So by factoring that out, you get fy and minus phi prime a, 1. Okay, that is the gradient vector of f in terms of d. Now, let us turn to the gradient of g. So by definition, the gradient of g is simply gxab and gyab. And again, since this is non-zero, let us factor that out, gyab. The first term becomes gx divided by gy, and the second term is 1. According to implicit function theorem, we know that minus gx over gy is phi prime. So this guy is simply minus phi prime of a, right? So see that these two vectors are actually parallel. They share the same direction, right? Only they have the different magnitude. So you can write it out. Gradient f is indeed some multiple of gradient g. And then we usually refer this multiple called lambda as the Lagrange multiplier. Okay? So that is basically a proof. Basically, whenever you have a implicit function theorem, then everything just goes smoothly. It's a powerful kind of tool in calculus. Okay, so let me go back here. Again, the proof is not that important, but the concept is. So basically, Lagrange multiplier tells you that if f achieves local extrema on some constraint, then you have an additional set of equation. Instead of finding the critical point itself, you have to solve this equation. Gradient of f must be parallel to gradient of g, right? So the first example I'm going to provide is to demonstrate the importance of this condition. If nabla g or gradient g is 0, then this multiplier theorem might not hold. So here is it. We're asked to find the minimum value of this function, f of xy equals to x, a rather simple function, on this curve. Y squared plus x4 minus x cubed is 0. So first of all, we notice that if I rearrange this equation, then y squared must be x cubed multiplied by y minus x. And so we must have x strictly larger than 0. larger or equal to 0. Because whenever x is negative, then this guy is negative, right? Oh, my bad. When x is negative, then this guy is negative. So this whole thing will be negative, and therefore it is not consistent with the equation because y squared is always positive. So x is always larger than 0. And of course, x can be 0 because there is some point 0, 0 that is on the curve. Okay, so consequently, obviously, this function has its minimum as 0 because you cannot have negative x, right? So the minimum possibility is 0. So the minimum is achieved at a point at f0, 0 being 0. However, if you look through the gradient, you see that the gradient of f at 0, 0 is actually 1, 0, right? On the other hand, the gradient of this curve is given by, actually, let me write it out. The gradient of y squared plus x4 minus x cubed is minus 3x squared plus 4x cubed, and then 2y. So if you plug in y and x being 0, then it is a 0 vector. So you see that these two guys are actually not parallel. These two guys are actually not parallel, right? So that suggests that whenever the gradient of the constraint is 0, then the multiplier theorem will not work. But this is a very special case. In most cases, the multiplier theorem works. This is just a counterexample to demonstrate why is the gradient of the constraint being non-zero so important. Okay. Yeah, so let's start our example. Actually applying the Lagrange multiplier method. So this example tells asks us to find the extreme value of this function, f of xy being x squared minus y squared, subject to this equation, x squared plus y squared equals to 1. So obviously there is some elementary method to do this. For example, we can parameterize x and y by cosine theta and sine theta, and then plug it inside, so everything becomes a single dimensional, single variable calculus. But in this case, that just protects the general system of the method of Lagrange multiplier. So by setting g of xy to be by setting g of xy to be x squared plus y squared, we are having these equations. First of all, you must have that being 1, right? Second of all, by the Lagrange multiplier theorem, if you want to achieve a local extrema, then the point has to satisfy this equation. Gradient of f has to be parallel to gradient of g up to some constant lambda. So writing down everything, you have 2x minus 2y is equal to lambda 2x 2y. And same thing happens here. So x squared plus y squared is equal to 1. Okay, so first note that again, the method of Lagrange multiplier is applicable because now log g of xy, which is this guy, is never 0. The only possibility that this vector is 0 is when x and y are both 0, right? But that is not valid because 0, 0 is actually not on this curve. So on the curve, the gradient is always non-zero, right? Okay, so yeah, so we can apply our Lagrange multiplier, basically trying to solve these two equations. So we can do that whatever you like. Based on the first equation here, I prefer to analyze the case where x or y is 0. When x is 0, then we see that by the second equation, y must be plus minus 1, right? And that corresponds to lambda being minus 1, and so you have two solutions, 0, 1, minus 1, or 0, minus 1, minus 1. Similarly, asymmetry tells you that when y is 0, then xy lambda is 1, 0, 1, or minus 1, 0, 1. And it actually is not possible for x and y to be both non-zero, because you can see that in the first place, if x and y are both non-zero, then you have 1 equals to lambda, and also minus 1 equals to lambda. So that is not possible. So the only four possible solutions are 0, 1, minus 1, 0, minus 1, minus 1, 1, 0, 1, and minus 1, 0, 1. So basically it corresponds to the four vertex of the circle, right? Like this, and this 4 vertices. So after evaluating of f, you get minus 1, minus 1, and 1, and 1. So the maximum of the f subject to g of fxy being 1 is given by this 2 point, and the value is 1. And the minimum of f of xy, subject to g of xy being 1, is this 2 value. And that is again, oh, this is -1, my bad. -1. Okay. Highlighting. Okay. So that's all. So basically, what you want to do is to solve this equation, the constraint equation and the gradient equation, right? So now we are not solving for gradient being 0. The gradient has to be parallel to the gradient of the constraint. And there's actually a really nice way to kind of make this into a systematic computation, which is a Lagrangian. So it is convenient to define this kind of function. We define L of xy lambda, a three-variable function, to be f of xy minus lambda, the additional Lagrange multiplier, multiplied by the constraint. So now it is g of xy being -1. And then actually the whole computation that we have just done can be reduced to gradient L being 0. Let us see why. So gradient L being 0 means that the three partial derivatives x, y, and lambda are all 0. So if you take the x derivative, you'll get fx minus lambda gx, right? The one here does not really matter. And similarly, you have fy minus lambda gy being 0. And if you differentiate by lambda, then it is simply g of xy minus 1 being 0, right? So you see that this kind of formulation actually provides us a really nice kind of intuition that you can extend the function into some other function that you are solving a critical point for that function. Okay, we will see more examples to see how this actually works, but you can see that as a first example, this equation is actually equivalent to this equation, where I should click actually. Okay, right, now let's do the second example. So in this case, I want to find the extreme values, maximum or minimum, of this function xy squared z subject to this x squared plus y squared plus z squared equals to 4. So that's a sphere, right? When we're learning spherical coordinate, there is also a kind of parametrization for this sphere. Sorry. So you can represent x and y and z using two variables, and then you can plug it back to solve these ultimate problem using a two-dimensional, sorry. Sorry, where was I? Okay. Yeah, so I'm saying that when we learn about spherical coordinate, you can represent the sphere in two variables, and that two variables can be plugged into this equation to solve for the minimum or maximum values. But before that, let us again do Lagrange multiplier. So I want to emphasize here that there's so many ways to find maximum and minimum value. Lagrange multiplier is interesting in a sense that it can be applied to most problems. So it provides a systematic way to analyze this kind of constraint problems. But I'm more than happy that if you can do like other methods to solve extreme value problems, okay? Right, so we define Lagrangian as I mentioned. This is the function xy squared z minus lambda, the additional Lagrange multiplier, subtract by the constraint x squared plus y squared plus z squared minus 4. So we ought to solve for the gradient of the Lagrangian being 0, which is equivalent to the gradient should be parallel, and the constraint should be satisfied. So you have y squared z being minus 2 lambda x, and you move that minus here, so you get 2 lambda x, and all the three coordinates gives you these three equations. So again, we want to verify if the Lagrange multiplier method is valid, and it is indeed valid, because the only possibility that the gradient of x squared plus y squared plus z squared, which is 2x, 2y, 2z, is 0, is when you are dealing with the point or the origin. But this point is not on the sphere, so we're good. Okay, to solve this equation, again, there's so many ways to solve it. I tend to analyze the easiest case first. So for example, when y is 0, then this means that um, here, here, you see that the left-hand side is 0, right? So we get 2 lambda x and 2 lambda z are 0. So either lambda is 0 or both x and y and z, x and z are 0. But this is not possible because that means that x and y and z are 0, which is not on the sphere, right? So the only possibility is when lambda is equal to 0. And so for every x and y and lambda being 0, x and z can be solved like this using the fourth equation, right? So this will be the general solution when y is equal to 0. X, 0, plus minus root of 4 minus x squared, and 0, for every x belongs to minus 2. And although there are so many critical points, but actually if you plug it in the function, it gets 0. The function actually looks like this, right? xy squared z. Since y is 0, so this is always 0. So among this all critical points, the function value is actually 0. Right. Now let's consider the case where y is non-zero. So y is now non-zero. And so by the second equation, we see that we can divide y by both sides, right? I want to kind of emphasize this again because we haven't do list math algebra before. You cannot cancel out a variable on two sides without assuming that it is non-zero. So for example, 2xyz equal to 2 lambda y does not mean directly 2xz is equal to 2 lambda because y might be 0. If y is 0, then the quantity I just mentioned might not be the same. So in this case, y is non-zero. You can actually divide y on both sides, which we get lambda equals xz. And if you plug this lambda back into 1 and 3, for example, this first equation tells you y squared z is equal to 2 times xz times x. So then you get y squared z equals to 2x squared z. And similarly, xy squared is equal to 2xz squared. Now, let us solve this equation, the fifth equation here. So again, I break the case into several cases where x and z are either 0 or not. In the first case, where x and z are both 0, then directly from the fourth equation, we know that y is plus minus 2 because x squared plus y squared plus z squared has to be 4, right, on a sphere. And if x is 0 and z is non-zero, then we see by this equation that the y squared is actually equals to 2x squared, right? You can divide z from both sides. However, x is 0, so y is 0. And that is a contradiction because y is non-zero based on our setup, right? And I want to make sure that you understand this notation. This is called a contradiction, meaning that this solution is not possible. And we use this notation because this is an arrow like this. And then we abbreviate by this notation, okay? Contradiction. Right. And on the parallel side, when z is 0 and x is non-zero, you can also conclude that y must be 0. But again, that's a contradiction to our assumption here. Lastly, when x and z are both non-zero, like that, then by the first equation here, you have y squared equal to 2x squared, right? By the second equation here, by dividing both sides by x, you get y squared equals to 2z squared. So these three guys must be the same. Plugging that back in your equation here, so let me write down. If y squared is 2x squared is 2z squared, then this will be x squared plus 2x squared plus x squared equals to 4. Y squared z squared. Wait, I think I'm missing something here. 2x squared. Oh, yeah, that's good, yeah. So x must be what? Yeah. X squared plus 2x squared plus x squared is equal to 4. That means x squared is equal to 1. So x is equal to plus minus 1. And so y will be equal to plus minus root 2, and z will be equal to plus minus 4. So this tells us that you have 8 different combinations, okay? Like 1, root 2, 1, 1 minus root 2, minus 1, and so on and so forth. There will be 8 combinations. So it turns out that all the critical points that we have for L Lagrangian is this whole bunch of points, 0, 0, 0, 2, 0, and 0 minus 2, 0, and this 8 points. And now we can evaluate the function values. So let us recall that f of x, y, z is given by xy squared z. If you plug the corresponding points inside, you will get the first set is 0, and there is 2 collection that is 2, there is 2 collection that is minus 2. So the maximum actually happens at this 4 points. Sorry, this 3 points. Actually, this 4 points here. And this 4 points is the minimum. Okay? When I say plus minus, I mean 2 points. So 1 plus root 2, 1, and 1 minus root 2, 1. Okay? Right. So that should be like the first example of you guys solving Lagrange multiplier using the Lagrangian, right? And we'll do one more afterwards. So yeah, let me maybe go through here first. So basically, in conclusion, that if you want to solve Lagrange multiplier extreme value problems on a constraint with Lagrange multiplier, the way to do this is to set up the Lagrangian by f of x, y, z minus lambda, the actual Lagrange multiplier, together with the constraint g of x, y, z minus c. And we solve the critical points of L. Okay, now blah L has to be 0. And after having those many critical points, you plug those things back into the function f and to list down every possibility of the function value. The maximized will be maximum. The minimized will be minimum. Okay, for our next example, we seek to extend this algorithm to multiple constraints. So again, let me state the theorem first. If now you have 3 functions defined on a 3-dimensional space, and they're all differentiable, where f achieves a local extreme value, either local maximum or local minimum, on the set g of x, y, z being 0 and h of x, y, z being 0. I want to emphasize that this should be C and D, but I don't want to use too many notation because there's already a C here. So it does not really matter if there's a constant. If it's a constant, then you can simply shift this constant to the G or H, right? So whenever the gradient of G and the gradient of H are non-zero, and that they are not parallel, the gradient of H and gradient of G are not parallel at the point ABC, and that f achieves the local extreme on this constraint at the point ABC, then gradient of f can be a so-called linear combination of gradient g and gradient h, meaning that there is a lambda, some Lagrange multiplier, and mu is this now mu, like this, mu. So that gradient of f is equal to lambda gradient of g plus mu gradient of h. Okay, at a point ABC. And also this provides you an equation to solve x and y and z, right? So this is the proof is similar to the previous Lagrangian theorem, so I won't go through that, but let us start with the example. So in this case, it is a rather simple extreme problem. I want to maximize or minimize this subject 3x minus y minus 3z on a constraint x plus y minus z equal to 0, and that x squared plus 2z squared equals to 1. So the calculus afterward is pretty standard. We set up the Lagrangian L, X, Y, Z. Now there's 2 constraints, so lambda and mu, where this is the first function here, target function, minus lambda, the function here, and minus mu, the function here. Okay. Right. So now we solve for the gradient being 0, the critical point of the Lagrangian, and it turns out that you have 3 equations on the gradient part and 2 equations on the constraint part. So you have 5 variable, x, y, z, lambda, mu, and you have 5 equations. Again, we have to verify the validity of the Lagrange multiplier. So we see that, first of all, the gradient of this guy is never 0, right? It's a plane that is not horizontal. So actually, no, it is a plane, and it always has non-zero gradient. And the gradient of this guy looks like this, but this is only 0 when x and z are both 0. And that point is not on this on this curve, right? When you're plugging x and z being 0, the left-hand side is 0, so it is not on the curve. And so we can actually apply Lagrange multiplier, provided that this is non-zero, this is also non-zero, and these two guys are actually never parallel due to the y coordinate. Right, now you can see that let us solve this system of equation. And again, you have so many choices to solve. Let us do the simplest case. First of all, the second equation tells you that lambda must be -1, right? So now we already solve a variable. We can now plug in the first and the third equation, which you get mu x being 2, and that mu z is -1. So this two guys multiply together, getting a non-zero value suggests that mu must be non-zero. You can therefore solve x by 2 over mu and z by -1 over mu. And now we can solve mu by plugging those two guys, the sixth equation, into this fifth one. You get 2 over mu squared plus 2z squared, which is 2 minus 1 over mu squared, equals to 1. And you can then solve mu to be plus minus root 6. And then you have this fourth equation, right? Now we know x and z, we can solve for y. So it turns out that x, y, z, lambda mu can be solved in this order. So let me kind of go through this notation. Note that I use plus minus and minus plus. That means that there is two solutions here. One corresponds to plus root 6 over 3 minus root 6 over 2 minus root 6 over 6 minus 1 and plus root 6. And there's another solution in the down part. Minus, plus, plus, and minus. Okay, so there's exactly two solutions. And you can sort of imagine this while there's two solutions. This thing actually looks like a elliptic cylinder. So like this. It is an elliptic cylinder, and this is a plane. So basically, you cut through the cylinder, you get a ellipse, right? So this 2 points, these 2 points, is actually one of the two vertices of the ellipse. And so, yeah, you have 2 points. So you just plugging everything. You get that the function value at the point plus minus minus will be 2 root 6, and the other one will be minus root 6. So the maximized one will be the maximum. This is the maximum. And the minimized one will be the minimum. The minus 2 root 6 is the minimum of f constrained to x plus y minus z being 0, and x squared plus 2z squared equals to 0, equals to 1. Okay, I feel like I'm going a little bit fast today, but let me kind of summarize what I've done. So in this section, this is a generalization of what we had done in the section 14.7, which is finding a local extrema or absolute extrema of a function without constraint. In this section, we have a particular constraint. It usually is in the format of some function equal to some value. Okay, so like this or like this. So based on that intuition, you cannot really solve the critical point of f itself, because the critical point might not be on the constraint equation. So alternatively, we have this Lagrange multiplier theorem, which tells you that whenever f here achieves a local extreme on a particular constraint, then the gradient of f must be parallel to the gradient of g. And that motivates the method of Lagrangian, tells you that we can set up this type of new function, a variable, an additional variable, so that you are, instead of solving the critical point for f, we're solving the critical point for L, which accounts to the parallel of the gradient and also the constraint itself. And a really nice thing about this is that it generalizes to high dimension set and also multiple constraints. We see that in this case, we're dealing with a 2-dimensional function with one constraint. In this case, we're dealing with a 3-dimensional function with one constraint. In this case, we're dealing with a 3D function with 2 constraints. So it is actually really systematic. Basically, you follow the algorithm. You set out a Lagrangian. You find the critical point for Lagrangian, and then you verify whether those points gives you maximum or minimum. And that's all. Okay, so yeah, Congratulations, you guys have finished the differentiation part of the high dimensional calculus, and we're now going to investigate the integration. So that will be chapter 15, I think. See you guys.